Thank you, Ji and Camilla, for the kind invitation. I'm very happy to be part of this distinguished lecture series in IT Universal Technology. Today, I just want to what impact of move towards nutrient in a circular economy. So I just want to thank you for my colleagues as well as the students for last 5 years who have been involved in this project. Dr. Sharupuncho, Leonard, Ibrahim, Pema, Federico, Jerry, Jade, Umakan, and Abdul, Wanjung, and Haoyu. So they have contributed some of our result and discussion for this slide. So these are today's contents. I want to share with you a clear concept of a circular economy and resource recovery. And nutrient, what's the linear and circular economy? So we have investigated the urine challenge and opportunity for the last 5 years. So happy to share this kind of information, how we can create the sum of the nutrient resource recovery and what's the gap to reach the marketable urine technologies. Also, what we have developed at UTS. Also, we have successfully get the sub-ARC research hub in a circular economy, which is called ARC Nice Hub. So I want to briefly introduce what's this objective and vision, and then how we want to organize this hub. So we look at the possible collaboration. So if you're interested after this presentation, so please contact us and we are happy to work together. And what are the case studies in the world for the nutrient resource recovery and take-home messages? So the economy is very linear at this moment. So we just simply take resource and then make and use and dispose. So this is the very linear economy situation. So we have to make sure that the circular economy. So you can see the different kind of material we are just to dispose, like after uses. So airplane, cars, and building material, electronic devices, also plastics and textiles. So this kind of economic model is putting our life system under immense pressure, so especially exponential population growth and then resource consumption are accelerating this kind of the climate crisis, also biodiversity losses and overuse of the natural resources, leading to a lot of problem for our waste and pollution. So we do have to do something. That's the reason why we have investigated what could be the possible way to make this kind of problem to have a solution as a circular economy. So circular economy is a economic system that tackles global challenges like climate change, biodiversity loss, and waste and pollution. And on the other hand, the resource recovery is using the waste as an input material to create the valuable product as a new output. So resource recovery is a subset of a circular economy. So if you look at this diagram, so you will have a more clear, we consume and then try to minimize waste, also collect and sort waste, and we recycling. So we have done a lot of recycling reuse for last 20 years. So people sometimes very much confused. So what's the difference from circular economy and recycling? So that's the very big difference because we need to go through another in-depth and complicated resource recovery system. So this is what we have done for last more than several decades, recycling reuse. So we try to less natural resource, maximize the recycling, minimize the waste. But in the future, this kind of recycling and reuse are not enough. So we want to have a more sustainable concept, which is a circular economy. So this circular economy, how we can design for this kind of recycling, reuse, and manufacture for circular economy system. So manufacturing is the another new challenge we have to achieve this circular economy. So still, if we are confused, you can think about the plastic bottle or just wine glass bottle. So we used to utilize this kind of plastic or wine bottle, and then we have used recycling. So we just clean up or wash and then reuse the wine bottle or plastic bottle and then recycle. That was the we have done for last several decades, but in the future, this recycling is not enough. So we need to make sure new manufacturing system because this kind of bottle, plastic or wine bottle, some of them are cracked, some of them are broken, some of them are damaged. So that we need to let them look at some different way of the recycling and manufacturing system. So we can melt this plastic and then create some of the plastic bag or some of the uh, plastic cassette. So that that's the one of the new concept of the manufacturing we can achieve using this circular economy. So making sure there is a myth between recycling or reusing and circular economy. Circular economy is further in-depth and then complete concept we have to generate as a new manufacturing system. By transitioning to this circular economy, so Australia could generate 2 billion or 3.25% of GDP in direct economic benefit and save 160 million tons of CO2 by 2040. So in this presentation, I like to mainly focus on linear economy for the nutrient cycle. So if you see this nutrient, how we consume and how we dispose, so you can see we create the nitrogen from the air, so nitrogen fixation. So you need 1,000 degree of the temperature and 100 bar high pressure, so that the 2% of global greenhouse gas emission required to make this kind of nitrogen fertilizer. On the other hand, the phosphorus is one of the important fertilizer. So, however, this is the very limited reserve. So this will be running out in 100 years. So we have to find the alternative phosphorus fertilizer material, or we have to generate some of the supply economy system to save. So we produce the fertilizer and grow some food, and then we consume. So we can discharge this kind of nitrogen phosphorus into environment. So in what ways the nitrogen phosphorus create some of the pollution to create some microalgae blooming problem. So we have to remove the nitrogen phosphorus before we discharge to the environment. Also, this kind of material will create the CO2 and N2O because we need to remove in a wastewater treatment plant. Also, some of the leaching and runoff will create another environmental ecosystem. So this is the current nutrient cycle, which is the very linear economy. So if you look at what's the fertilizer market and the urine, how much fertilizer we contain in these sources. So urine holds enough nitrogen and phosphorus and potassium to offset the more than 30% of the agricultural fertilizer demand. The value of those recovered nutrients would equal to US around $13.6 billion annually. So this is the potassium and then phosphorus, and this is the nitrogen fertilizer. So you can see the $2.3 billion, and also phosphorus 2.3, and then nitrogen is $9 billion revenue we can create from our urine annually. Also, if you look at the global fertilizer demand, it's keep increasing. And then nutrient in wastewater. So we discharge a lot of nutrient in the wastewater. So 6.3 teragram potassium, 3 teragrams for phosphate, and 16.6 teragrams of the nitrogen. So nitrogen demand is keep increasing. So you can see the different continents, Oceania and Asia and America. Asia is keep increasing further compared to the 50 years ago. And then Oceania also, we have used our nitrogen fertilizer a lot, almost 8 times higher. So you can see the how much we create this nitrogen and then consume. So this will require the more sustainable source finding. So we have to look at how we can also look at some of the nutrient circular economy system. So urine has a very high concentration of nutrient. So in wastewater, urine has a less than 1% of volume, but the nitrogen concentration is almost 80%, and phosphorus 65%, micropollutants such as the pharmaceutical or endocrine disruptor chemical is more than 50%. So if we source recover for our urine, so we can enhance the food security by recovering the nitrogen and phosphorus. So you can see the how much nitrogen, phosphorus we can create. So you can compare with the feces and urine. The feces has a lot of solid material, so that you have a less nutrient, nitrogen and phosphorus compared to the urine compound, so that we can create the more food security and reduce the energy associated with the fertilizer process, which is the Haber-Bosch process. So require almost 2% of the global electrical energy consumption. Also, we have a nutrient removal for nitrification. So you need aeration to remove the your ammonia and then nitrogen compound. So you need a lot of energy consumption for this wastewater treatment plant. So we can reduce if we make sure that this urine diversion also reduce the water consumption by reducing the flushing and improve the overall water quality, because we reduce the overall discharge of the nitrogen and phosphorus into waterways. So this is the way how we can create this circular economy. So we produce the food and then consume and collect the nutrients as a fertilizer, and then we can continue to close this loop to make sure that our sustainable nutrient cycle. Also, if you look at the nutrient balance in Australia, so this is the $1.5 billion market. So nitrogen 1 million ton, phosphorus 4 million ton, and then potassium 0.2 million ton. However, we just lose most of fertilizer because they are very small molecule, and then easy to diffuse into the water and then just to penetrate the groundwater. So more than 50 to 60% agriculture, food processing, and waste losses, that we just export 25% to food, and we utilize domestically and only 20% of our agriculture sector. So we have to make sure that how much we can reduce the fertilizer losses from this kind of market. So this is how we can create the value for United Nations Sustainable Development Goal. So if we achieve this linear economy to a circular economy, so we can contribute to our SDG, sustainable cities and community, in terms of food and nutrient recycle, and the climate action. We can reduce almost 50% of the climate action based on this fertilizer, and then life below water, and we can also responsible consumption and production. Also, we can clean the water and sanitation, as well as we can produce the food from our fertilizer, so that we can contribute more than 6 SDG from this nutrient to circular economy system. So let's look at who is doing the urine diversion internationally. So you can see the Swiss Federal Institute. They have developed this one for last also 10 years, and Sweden, US, also a lot of institutions, they are trying to create the more value from our waste. So I can show some of the case study at the end of this presentation. Also, we can collect our urine. So we have a waterless urinal toilet as well as a pedestal toilet. So you can see at the front, you can collect your urine using this pump. Also, this is the new generation of the urine diversion toilet. So this is the urine, and the urine is slowly pass through this surface and then goes to this pipeline. And the other hand, we have some solid can pass through this pipeline. So we can effectively separate urine from the male urinal as well as the female pedestal toilet. So this is possible. We can install and then collect the urine and the other solid material effectively. And this is our fresh urine. So how this urine can be converted to the fertilizer. So there are a little bit of chemistry involved this one. So when you urinate, so you can see the very much yellowish color, which is the fresh urine. So this is fresh urine is based on urea. So urea, mostly they have this yellowish color. And then when you hydrolyze, so it changed their urea to ammonia and then some of the different material because of the pH. So we produce the struvite, which is one of the solid fertilizer, magnesium and ammonia and phosphate. So combining together, and then you can create the struvite stone. So already you know some of people have a kidney stone. So this is the kidney stone. You can think about some people exposed to their urea to hydrolyze, and then they create this kind of struvite stone in their kidney, and then you can see their precipitated struvite fertilizer. So after you hydrolyzed one, and then a lot of microorganisms will survive in your hydrolyzed urine, and then this will create another nitrification. So if you look at the molecule change of your urine material, so mostly urine contain urea. So you can see the ammonia and carbon and ammonia compound in your urine. And then when you hydrolyze, because of aging or urease or some of the microorganism contact, so you created ammonia, and then this ammonia, they join the one more hydrogen. So this hydrogen creates the more high pH because they lose their hydrogen into ammonia to ammonium ion, so that you have a very high pH, and then this high pH will precipitate with the ammonia and phosphate and magnesium. So you create the struvite, and this ammonia will convert when you have a microorganism. We just say that this bacteria, nitrosomonas bacteria, nitrobacter bacteria, will convert ammonia to nitrate and nitrate. So when you have your urine, fresh urine, urea can be a fertilizer, but this is not stable. And then we need to convert this urea to nitrate and ammonia. This is the more stable fertilizer, so that you can make sure that your fertilizer is a very stable condition. So based on this chemistry of our urine, So we want to target this nitrate and ammonia as a stable fertilizer. So how we can maximize this compound in our urine. So that's why we have developed the technology to convert to urea, to ammonia and nitrate. So if you look at some of the marketable urine technology, Struwide, already there are some market for this solid fertilizer and nitrification, biological treatment process, liquid fertilizer, also ammonia stripping. The ammonia can combine with the hydrogen sulfate and then create the ammonium sulfate as one of the high quality of the fertilizer. So these are currently available marketable fertilizer. However, still we need to develop the more efficiency of the how we can get the better quality of the fertilizer, and then how we can make sure that the safe fertilizer. That's the challenge we have to look at in our study for last 5 years. So we have collected our urine from our university building and Faculty of Engineering. So we have produced 1,000 liters per day. And we look at how we can recover water and nutrient and energy from this urine source and apply to the space, because space they produce the urine and feces and wastewater has to be also combined with the sum of the application for water and nutrient. Also hydrolyze the urine, diluted fresh urine. Also power generation is possible because of different salt concentration. So urine has very high salt, around 20 grams per liter. So based on this salt difference, so we can apply for reverse electrodialysis and then produce the hydrogen from these electrodes. So that's the power can be produced for hydrogen as well. Also biomass, so algae can be grown from this nutrient of our urine. So urine is a good fertilizer. So we can put the algae and grow some of this algae and then change to biodiesel or some of the biomass application. This is the 5 different applications we have developed for last 5 years. But in this presentation, we want to focus on this hydrolyzed urine, which is the most close to the research translation, as well as the good application point of collaboration. So we have developed for last 5 years for this hybrid membrane bioreactor and membrane distillation for the production of the liquid fertilizer. So we collect the urine and then we combine with the biological oxidation process and we concentrate using distillation. So what's our smell? So people do not like their odor and organic in urine. So how we can remove this kind of material? And the ammonia, as we discussed, ammonia has to be converted to nitrogen as a stable fertilizer solution. Also, treated urine can be applied to the commercial fertilizer level. So we compare with the commercial fertilizer and urine fertilizer, and then how this is the difference to grow some of the food, such as lettuce and bok choy. So that's our initial question, and then we delivered some of the experiments. This is our university 15 story. So we collect the urine from male toilet, and then at the basement 3, so we have a urine facility, and we have collected our urine from this urine pipeline, and then we connect the membrane bioreactor, which can remove the organic or some smell, and then acidification ammonia to nitrate, nitrification conversion to make a stable fertilizer, and then we distillate to make sure that the concentrate, because of transportation purpose, so you can make almost 100 times or 200 times less volume of the water. So we can create the very concentrated fertilizer. Also, distillation can make some of the additional sanitation issue also can remove some smell and odor. And based on that, we have a trademark of the oval, which is the urine is valuable and you are valuable. So based on that, we have tested some of the lettuce and the pak choi. And then I want to share more detail. So Mbr Performance. So based on our urine, urea effectively converted to this ammonia to nitrate. So we have a conversion rate of the 50% using our membrane bioreactor system. Also, most of organic, which is very smelly compound, odors, can be removed more than 98%. So we have successfully developed this membrane bioreactor system. And then we try to concentrate this urine. So you can see how much urine can be concentrated based on the urine concentration factors. So you can see that when you have more than 80%, which is this is the fresh urine, and then concentrate urine, and this is the permeate from the distillated urine. So you can see that we could achieve almost maximum 95% of your urine fertilizer from the fresh urine. But we have a too much membrane fouling issue, so that we practically decide to have 80% of concentration to produce sustainably this concentrate fertilizer. So this is our trademark. You overall the product composition. So this is the overall total dissolved solid conductivity concentration, 250 milligrammes, so which is almost 200 gram per liter of concentration. So seawater is around 3.5% of salt concentration. So we can achieve our fertilizer more than 20% of fertilizer solution. The pH, the ammonia and nitrate concentration is almost 60 gram per liter, and phosphate is around 5 gram per liter of the concentration, and then some of the potassium, 17 gram per liter of concentration we have obtained from our Mbr and the distillation process. And based on this fertilizer, we have collaborated with the Royal Botanic Garden in Sydney, and then we look at the hydroponic system to grow lettuce and pak choi. And this is the standard fertilizer. And this is the commercial fertilizer optimum. And this is our urine fertilizer produced from our university. And then we look at the very much comparable result. Also, this is our conclusion. So based on our technology, Mbr and then distillation, the 90% of the TOC removal, the odor can be removed, and 50% ammonia and nitrate, which is the very stable condition of our fertilizer, and 95% of urine concentration can be achieved, and then ammonia 97%, others rejection is 99%, and then urine can grow some of our vegetable, lettuce and pak choi, compared to our commercial fertilizer. So this is our laboratory scale, and this is our pilot scale, 100 liter at the basement of the building 11, and this is our concentrated fertilizer. So we have developed this product from our membrane bioreactor and distillation process. Also, we have tested some of the vegetable. So this is the parsley. So you can see this is our product, urine fertilizer. This is the commercial fertilizer. So we can see almost the same performance of compared to this commercial fertilizer to grow this parsley. As well, also we have a collaboration with the Royal Botanic Garden, Sydney. Also, we utilize the leaf terrace. This is what kind of cactus of the South America. So this yellow color is our urine fertilizer. This white color is commercial fertilizer, which is the Calmec grower. And then we found out that our fertilizer is very much comparable with the commercial one. Also, we have tested commercial fertilizer power pit with our fertilizer. Then we found out the coriander and the basil had a very much similar performance of the overall growth, as well as we tested a very simple. This is the DI water only, and this is our urine fertilizer and commercial fertilizer. And definitely, yeah, we found out some of the advantage of the urine fertilizer because there are a lot of mixture of the fertilizer, so that some of the plant grow better than commercial fertilizer. So that's what we have tested for this kind of vegetable. So now is in the future we look at the more bigger scale with the collaboration of the Botanic Garden as well as the City of Sydney. So some of parks we look at the long-term application of our fertilizer. So we have liquid fertilizer as well as the solid fertilizer. Then how we can apply to the park in the City of Sydney as well as the Botanic Garden, and then we will try to see the long-term benefit of our fertilizer compared with the commercial fertilizer. So based on this result, so we apply the ARC industry hub for nutrient in a circular economy in 2020. So this project is a key partnership to transform the wastewater industry and build the confidence for a market in reusing wastewater and urine as a source of fertilizer for agriculture, horticulture, and parkland. So we have 4 major research themes: how to collect effectively, as well as the toilet manufacturing, regulator, and operator. Also, how to convert this urine to fertilizer. So how we can make very cost effective and then simple technology to convert our urine to fertilizer, and how to optimize. So there are urine fertilizer can make a better function in some of your plants or vegetables. So how we can make optimization of fertilizer, and then how we can use this application as a horticulture, agriculture, also some of the parks and gardens. At the same time, we look at some of the economics. So how this is economically viable. So we look at the detailed economy from this project. Also, we need to educate circular economy for nutrient cycle. So engagement, education, and learning and communication are all our also objective of this ARC industry life hub. So we have 7 universities: Melbourne, Griffiths, Western Sydney, and Southern Queensland, Victoria, and then Queensland University. And they are working together with the different industry partners. So we have 22 partner organizations. So I very much appreciate their cash and in-kind contribution in terms of different research themes. Also, we have 3 international organizations: EWA, also UNIST, also in the US, Rich Earth Institute. So we have collaborating together to learn each other for their experience, also how we can make this technology for real translation and commercialization opportunities. So we have a different application scenario. So Melbourne University and Brisbane, they are very much focused on direct use in parkland. So there are some parkland in the Brisbane city. So they want to install their technology in a public toilet and then produced on the spot and apply their fertilizer directly to the garden. So Victoria Garden can be grow some of their turf. That's one of our objectives. As a Sydney node, as a UTS, we are very much focused on building level of our application. So this is our university. Already we have a very fantastic infrastructure, and we have collected our urine, and every day around 1,000 liter. And then how we can convert this urine to fertilizer and then deliver to this one to the farmers and some of the flowers and horticultural application. So that's what we are planning to do. So these are two applications. We look at how we can make some kind of sustainable operation system. So this is uh, our overall economic benefit if we use this urine diversion system. So 75% urine diversion, so we can reduce the 30% reduction in energy cost in a wastewater treatment plant. Also 75% urine diversion, up to 60% reduction in energy cost is possible. Also 50% reduction in the freshwater demand because we don't need water to flush your toilet, especially for urine, not the other solid, and reduce the wastewater footprint and increase the capacity of the existing wastewater treatment plant and new industry and jobs for urine businesses. So that's what we have published for last 5 years. Also, this is the study from the University of Michigan, life cycle assessment for urine diversion, and they believe the urine 90% diversion, the wastewater treatment plant can reduce the 40% in greenhouse gas emission, 50% of the freshwater use, 45% in eutrophication potential can be reduced. So that's what we have an environmental benefit from this urine diversion. Also, we want to expand our activity, not only urine, but there are a lot of nutrients can be discharged in urban wastewater, industrial wastewater, livestock wastewater, and then the anaerobic bioreactor produced a lot of nutrients. So we try to collect as much as we can to reduce the overall impact of this fertilizer process, and then convert to our nutrient to fertilizer to grow edible crops, better environment. Also, some of the green building and top glass can be applied using this kind of quality of fertilizer. So that's the overall our research project will deliver next to 4 years. And this is the one of us, our objective. We can create this kind of nice blue toilet. The public toilet can combine with the growth of some flowers, and then we can directly apply to our urine to grow some of the plant. Also, some Paris in France, so they have a direct urine fertilizer application using solar drip. So this is the solar drip bottle. So you put the 20% diluted urine. So you can just put there into the soil, and you can use water as well as the fertilizer. So that's how we also try to combine as an individual application of their very safe urine application. So they have tried some of the tomatoes. And this is the application from Sweden. So they applied to some of the barley, and this barley is the raw material of the beer, and then they produce the beer from the urine fertilizer, no fertilizer, and then commercial fertilizer, and then they found out the better quality of our urine fertilizer compared to the different fertilizer, and they have produced the beer from this kind of the barley application of the fertilizer. Also, some of the park application of the small scale in Cornell University. So we have also individual bottle. So we also try to advertised our small scale, like a bottle-oriented your urine collection system. So every university student, also some of the community, can collect the small scale from their own urine, and then we can have a centralized our urine processing technology, and then convert to fertilizer, and then we can give them fertilizer. So that's the one of the circular economy concept. We can work together with the student as well as the communities, and this is the application of their garden in Cornell University. Also, this is the hemp industry, how they apply to this fertilizer. And in the future, yeah, that's our nutrient cycle prediction, also public perception. So if you look at our nitrogen or phosphorus, so this is our prediction. So we are in 2020 here. So if we don't try to recycle nutrient or try to look at the nutrient circular economy, so it will keep increasing the nitrogen, which will damage our environment as well as phosphorus. But if we convert our waste fertilizer from wastewater treatment plant or wastewater urine, as well as some of the nutrient sources from industry wastewater, as well as livestock wastewater. And then we can try to slow down increase of the release of nitrogen into the environment, that we can make sure that the sustainable nutrient fertilizer application for the sustainable pathway of the social technical approach. Also, we got a result from the wild Chess Alder. She investigated the are you happy to eat the urine grown vegetable? So she asked more than 3,700 people at the university in 16 countries. So this is the global average, 59%. They are happy to have a vegetable grown from this urine fertilizer. But still, yeah, there are a lot of less than 50%. So that this AIC hub, that's the one of our objectives. We want to increase the public perception to make sure this is the environmental friendly, economic friendly, and that they will have a better public perception in the future after this AIC hub. So hopefully, after this project, global average, we can increase up to 70%, and then slowly also we can make a better acceptance of this urine fertilizer in the future as a nutrient in a circular economy system. So I want to conclude this presentation. So you are very clear about what's the circular economy and resource recovery and recycling. So recycling has been for last more than several decades, but now this is not enough to make sure that our climate issue as well as our recycling opportunities. So we need a different concept as a circular economy will benefit to our climate change as well as environment. So urine is liquid gold, and urine diversion can do food security, energy reduction, and water reduction. And urine diversion benefit climate change, circular economy, nutrient resource recovery, eutrophication, wastewater infrastructure, and social, technical, environmental, economic, political issue can be also resolved in the future. That's the reason why we need your support to make our concept to promote to the others and community to make sure better public perception, and that education, feedback, and advocacy will help to make a sustainable translation of this technology. Also, we have a official launch of the ARC Hub, and second nice summit on 17 November will be held, so that if you have time and if you are more interested in this circular economy system, So please join us our summit and launch, and we are happy to collaborate together. So that's we will send you the registration. So if you are interested, please send the email to me, and acknowledge it to our student, there's 12 students, and then research staff and lab technician staff have been involved in this project to reach to this level. And then also we have a CI, PI, scientific industry advisory committee members. So they will also work together for next 4 to 5 years to develop this nutrient in a circular economy. So please join us if you're interested. Also, school and faculty research office always very much supportive to have administrative as well as the infrastructure and our overall support of this project and research. Also, ARC Nice Help, it's ARC funding is very much feasible to make our collaboration with the industry partner as well as the university CI. So thank you for your attention, and I very much appreciate looking forward to working together in the future.
Thank you, Sean. It's an excellent talk. Even I'm not in your area, but I have learned a lot. It's really this very significant, highly impact research area. It is an excellent research center. I believe you will have high impact generated. Now it's time for questions. Any questions?
Yes, Jilu, is VG?
Yeah, how are you?
Good. You can offer Sean a laureate fellow.
Yes.
Okay. So coming to the questions, Sean, as usual, your presentation has been excellent, very convincing. I have a couple of small comments. You were saying that urine has nitrogen, phosphorus, potassium, and also the micropollutants such as pharmaceuticals and personal care products.
Right, that's right.
How are you? I saw your proposed diagram. You are going to use the Mbr followed by the adsorption, which is an excellent concept. And you also were saying in your Mbr that you have the flux decline. So why not you combine the Mbr with the adsorption together as a single process by which you could reduce the fouling, and also you can remove practically all the micropollutants.
Thank you, Vicky. That's the correct. Your concept is very much, we are also on the investigation. So you want to put the powder activated carbon or absorbent in this system, rather than separating the some other absorption column or some other additional process. So that's correct. So we have a student like Jade Jiang. She has investigated this concept of the absorbent with the membrane bioreactor to reduce the overall space as well as the removing some of the micropollutant. So that we have several publications on the review, so that we can share. You are correct. So you can give us also some of the collaboration. You have a lot of experience from the PAC activated carbon membrane bioreactor to remove this kind of contaminant. So we are happy to also work together with you in the future for this kind of development. So that's our next step, to make a very small and compact membrane bioreactor with the activated carbon.
You have been helping me also on that when you were student one. Then one other very quick question about this nitrogen availability. Would all the nitrogen you produce in the urine would be available to the plants, or only part of them?
All right. So that's the very good question, which is relevant to more about. Just let me show you. Share that. Yeah, this one. So nitrogen, phosphorus, and potassium. So they have a different uptake from the plants. Some plants, they like to uptake from urea, some of them ammonia, some of them nitrate. That's the reason why most of fertilizer, they are mixed version, like combined with ammonia, nitrate. It's a very much common fertilizer because the summer plant, they can observe cation like ammonia and anion, the nitrate, the nitrogen compound. So some of, depending on the plant, they have a different uptake rate in terms of different nitrogen forms. The urea form, ammonia form, also, even though I mentioned about only ammonia and nitrate, the ammonia and nitrate is not only single compound, they have also combined with some other components. So that depending on what kind of count ion molecule, so that it's very much different from different plant, but definitely it's true. Every ammonia or nitrate cannot be observed by the 100% of the plant. So it's impossible to let them 100% observe nutrient as a fertilizer. So some of them, that's the reason why, as I mentioned in the some presentation, so this is the loss. 50–60% agriculture, food processing, food waste losses. So most of fertilizer, more than 50%, they are losing into groundwater, even waterways, because we cannot really control every fertilizer observed by your plant. So that's one of the researchers from the Melbourne University. They are developing smart fertilizer. So they don't want to release their nitrogen and phosphorus. So they just keep in the soil, and they're slowly releasing to your soil, and then they can minimize the loss of your overall fertilizer. So that's one of the research activity is going on, how we can minimize the overall loss of the fertilizer for nitrogen, phosphorus, potassium. So that's we have to also look at some of the opportunity to work with this area. So hopefully we believe that our urine fertilizer contain the carbon, there's some of the mixture, so that compared to the commercial fertilizer, which is just the synthetic ammonia and nitrate or urea compound, so we have a better stability of our fertilizer on the soil. So we will prove it through this ASC Nice Hub. So you will have a better answer after maybe 3 to 4 years based on our collaborator from Western Sydney University.
Thanks, Sean. Excellent presentation.
Thanks.
Any other questions? No? Any questions?
Jielu, I ask one question. Jesse here. So, Sean, thank you very much for your presentation. I can see you compare with your products with the available products on the market by planting some veggies and plants. So my question is, could we clarify your product as an organic product or organic veggies kind of thing? Yeah, that's my question. Thank you.
Okay, so you want to know about whether this is organic fertilizer, organic food, or biofertilizer, biofood, right?
Yeah, that's correct. Thank you.
Yes, yeah, that's correct, because this fertilizer is produced from human biosystem. So we have a biofertilizer because this is produced from human being as a biological system, so that we could say as biofertilizer as an organic fertilizer, so which is the environmental friendly. So that's your answer is yes, you're right. This is the organic and biofertilizers, and biofood can be produced from this fertilizer.
Yeah, thank you, Sean. Thank you, Jie. Yeah.
Thank you, thank you. So it is excellent. We have Sean to give this wonderful speech. And at the beginning, we thought, oh, maybe we organize a face-to-face, but because of the COVID situation, we still finally decided to have a Zoom. Hopefully, next lecture will be in person. And thank you very much for everyone to attend today's distinguished lecture series. And particularly thank you, Sean, for your wonderful presentation, including your wonderful design of your PPT. Thank you, everyone. Thank you.
Thank you.
Thank you, Gia,
Thank you.
Camilla, and thank you everybody
Okay.
to join this meeting. Thank you.